All right, my friends, sorry for the late start. So I just wanted to say a few more things about the Robinson Annulation, this sort of painful reaction where we can generate a fairly complicated structure from simple starting materials. So I want to review the mechanism and then talk about how you can recognize products that would have come from this. You can think about the Robinson annulation as its own thing, or you can think of it as a Michael reaction followed by an intramolecular Aldol reaction. The Michael reaction involves an enolate attacking the beta carbon, and the product of the Michael reaction is this 1,5-dicarbonyl compound. And I've been pushing you the past couple of lectures to pay attention to structural patterns in products, because that can help you remember how we got to those products. The 1,5-dicarbonyl compound, or a product with carbonyls that are 5 atoms away from each other, these are Michael products, and you could have made them via Michael addition. And the way to think backwards for a Michael reaction is to start at one of the carbonyls and go alpha, beta, gamma, and it's the bond between beta and gamma carbons that you could have made here in red via the Michael reaction. And of course, the carbon that's gamma to the purple carbonyl is alpha to the orange carbonyl, and that alpha carbon used to be an enolate. Okay? Then the intramolecular aldol you've seen before. You have multiple alpha protons to choose from. You're going to choose the one that gives you the most stable 6-membered ring product. The product of an intramolecular aldol is this beta hydroxycarbonyl compound, but for the Robinson annulation, basically always the observed product has the double bond between alpha and beta carbons, which we get by first making the enolate at this alpha carbon and then doing the elimination reaction to get rid of the OH group. Okay, so if you look at our product, I've highlighted in the product the bonds or the atoms that come from the starting material, this alpha-beta unsaturated ketone, and then this molecule that we used as our enolate. So these atoms in purple come from this starting material. These atoms in orange come from this part of the starting material. So it can be helpful to include among the things that we are looking for a structural pattern that's present in Robinson annulation products, and that is a 6-membered ring with a conjugated pi bond, a carbon-carbon pi bond, and carbon-oxygen pi bond. Another way of saying that is a cyclohexenone. So, you can put that on your list of structural patterns that you're wanting to recognize, cyclohexenone. Seeing these structural patterns is key to being successful on synthesis problems. So what I want to do now is give you an example of a molecule we could have made via the Robinson annulation, and I want to talk through how we determine what the starting materials were. So here is our product. Are you afraid yet with the 6-membered rings? Yeah? Yep, there's 3 of them. This is, I'm not sure what the right term is, whether it's aversion therapy or exposure therapy, but we are exposing you to your fears now so that you can learn to deal with them. Because fear leads to anger, and anger leads to hate. And
it leads to suffering.
On exams, yeah, exactly. Hate leads to suffering. So, all right. This is a product, and I want you to think what the starting materials would have been. And I might not even tell you that it was a Robinson annulation product. You would need to recognize that in this product. So look for this pattern, cyclohexenone. Looking for structural patterns allows you to narrow the problem down to simpler parts and allows you to ignore other things that don't matter as much. So where's the cyclohexenone? Well, here's a 6-membered ring, and there's the ketone, and there's the pi bond. All right, so right away, before going any further, I need to be experiencing a light bulb event like GRU, light bulb, where I see, oh, this is a Robinson annulation product. And right away, I'm going to be thinking, okay, this is a product we got from first step is a Michael reaction, and second step is an intramolecular aldol. Okay, so now the real work begins. Now that we can remember that a Robinson annulation is a Michael reaction followed by an intramolecular aldol, now we have to look for the aldol part of our product. So where in this molecule is the aldol product? What structural feature is consistent with an aldol product? There you go. Say it all together. No. The alpha beta unsaturated carbonyl compound. This is our aldol product. Which means and in that reaction we would have made these 2 bonds, right? So let's do this stepwise. Let's just think what the product would have been. And remember, the intramolecular aldol involves attack of an enolate on a carbonyl compound followed by, in this case, elimination to give you that pi bond. So what would the aldol product have looked like prior to elimination to generate the pi bond? What else would I have had here? The OH group on which carbon? Beta. And you know it has to be that because in the elimination mechanism you first remove this alpha proton to get an enolate, and then it eliminates to give you the double bond. Okay, well, we've thought backwards from alpha beta unsaturation to beta hydroxycarbonyl compound. Now, in an aldol reaction, and we've got this beta hydroxycarbonyl compound, which is the bond that we made in the aldol reaction, and what goes on either side? I actually feel like that was a lame Sunday school question, sort of a and then what happens question, all right? So clearly it's that bond, right? We all okay with that? It's okay if you're not, actually. So in an aldol reaction, recall that we have the enolate attack the carbonyl compound, and we get a tetrahedral intermediate that eventually gets protonated, and the pattern is a bond between alpha and beta carbons that wasn't there previously with an OH group on the beta carbon. So yes, this is the bond between alpha and beta carbons. Both the sigma and the pi are the ones we made in this aldol reaction. So let's think what would have been on either side of that bond that we just barely made. How about on our beta carbon? What should the beta carbon be? The one that has the OH group was what before the reaction? Carbonyl? Okay, good, because that's what gets attacked by the enolate. How about on the other side? What should that have been? Probably the enolate, right? Okay, so there's our reaction that would have generated the sigma bond, attack of the enolate on the carbonyl compound to give you the beta hydroxy ketone. And of course, we could get the enolate from just the corresponding ketone by removing this alpha proton. And we remove this alpha proton so that we generate, instead of this one, so that we generate the more stable six-membered ring. Okay, yeah?
In the textbook, sometimes it shows them coming from, like, instead of an intramolecular reaction, like a two-part, or I guess, like, out of two components instead of an intramolecular.
Right, you can do the Aldol reaction out of two components, absolutely. Yep. If you, in an intramolecular fashion, though, if you have the option for intramolecular, that's usually faster. So you're right, we don't necessarily have to worry about this enolate swimming off and finding another partner, perhaps this carbonyl on another molecule or that one, because before that will ever happen, these two are primed to attack each other. Yeah?
Oh, I guess...
Not your question, okay.
In the textbook, they commonly use, it's like, it very much looks like the group on the end there, but it's separate. It's like a 1-4, and then that double bond goes into help. It's like there's 3 bonds being formed.
Right. We're not done. You're right. There's another part. This is just what we have done so far is thought backwards through the intramolecular aldol step. But you're right. There's something else. Yeah, and we're going right there. Okay. So this molecule would have been our starting material. Okay. So we know that in the Robinson annulation, the previous step would have been the Michael reaction. And even if we didn't know that, we could pay attention to the fact that those carbonyls are 1, 2, 3, 4, 5 atoms apart. So this is a 1,5 dicarbonyl compound, or a Michael product. Okay, so let's now try to figure out what bond we make in the Michael product. I'm going to start with this carbonyl, and I'm going to go alpha, beta, gamma. And then I'll start with this one and go alpha. And we could continue on, but we won't need to. What we want to determine is which bond in this 1,5 dicarbonyl compound did we make via the Michael reaction. And so it might be useful to come back here and look at that Michael reaction that we drew to get an idea of which bond forms. Remember, an enolate, the alpha carbon of an enolate, attacks the beta carbon of this enone, or the alpha beta unsaturated ketone. And then we attack the beta carbon, the electrons move on to the alpha carbon where they're stabilized by resonance, and then they pick up a proton from water, and then you get your product with the new bond here between gamma and beta carbons. So back over here, that would mean this was the bond that we made, right? And so everything on this side would have been the alpha beta unsaturated carbonyl compound. And then how about on that other side? Let's draw what the alpha beta unsaturated carbonyl compound would be. Is this what you were thinking about? Yeah. Okay. And then how about on the other side? That purple gamma carbon or the orange alpha carbon, what should be on it prior to the reaction? Negative charge, right, because this would have been an enolate, and we would have had that enolate attack the beta carbon. Right. And of course, we could make that enolate by removing this proton. So, problem is solved. We now know what the starting material was, And we now know what both starting materials were. We now know that this was the molecule that we did the Michael reaction with, that this was the enolate, and that after the Michael reaction we did the intramolecular aldol to make not only this sigma bond, but the pi bond. And so going back to where we started with this problem, if you take the cyclohexenone and sort of count your way around the ring, the place where the double bond is, that's where you did the intramolecular aldol. And then on the other side, the bond between beta and gamma carbons is the one you made via the Michael reaction. Okay? So, go ahead.
Would it always have to be an enone? Or
Does it always have to be an enone?
like the beta keto ester?
Could you use a beta keto ester? You could certainly use a beta keto ester in as a nucleophile in a Michael reaction. If you're talking about using it as an electrophile, let's just draw the beta keto ester, and then I think it will become clear why you couldn't use this as an electrophile in the Michael reaction. And that's because there's no pi bond between alpha and beta carbons. And in addition, in order to do the subsequent intramolecular aldol, you need something with protons here so that you can make the enolate, which attacks that carbonyl. Yeah?
Last lecture you gave us like a ring problem with involving the Benzene products. A couple of meetings back. Would we be able to go over that this lecture?
I gave you a problem.
There's a synthesis involving like carbonyl with the chloride on it.
Yes, this was it. So this was in your notes. This is a couple of steps back. We were actually talking about the Claisen reaction and how you can use the Claisen reaction to make an enolate here that attacks the carbonyl, electrons kick down, and chloride leaves, and that makes this beta diester, which you can deprotonate and use as a nucleophile. This is now back. This step is now back from chapter 17 or something, enolate alkylation, where the enolate attacks the sigma star, the antibonding orbital between carbon and bromine to make a new carbon-carbon bond, and then you remove a second proton, the other proton here, to make a new enolate, which also attacks the other Br, and you will have made a six-membered ring. Then you do ester hydrolysis and decarboxylation and tautomerization to get to that product. So this will be, if you need to look through that in a little bit more detail, this is in the notes that I posted from last time's lecture. All right. So why even worry about this? Oh, go ahead, please.
When you're deciding how to make the starting materials for the Michael product,
Yeah.
how do you know which carbonyl to count? Carbonyl,
good.
alpha, beta, gamma.
Good question. So I knew what I wanted the starting materials to be, so I chose this way. And the way you will do that is to try to get in my head and guess what I'm thinking. I'm just kidding. That's not the right answer. Right. So I think what you're pointing out is what if I numbered this differently, right? What if I said alpha, beta, gamma, and said, well, could I have made this bond via the Michael reaction? All right, so if we did that over here on this side, we would have had this enolate. And then on the other side, let's see what we would have had. So we would have needed an alpha-beta unsaturated carbonyl compound with a double bond between alpha and beta carbons. Is that possible here? No, the presence of the methyl group sort of makes that so no good. If that weren't there, could you have broken it apart differently? Yes. And the standard is always, if your chemistry works, you get the credit. Even if I count it wrong at first, you can always come tell me and show me that your chemistry works, and then I'll give you the points for it. But yeah, in this specific example, the fact that the alpha carbon is bonded to 4 things already, there's no room for a double bond, which means this side could not have been the alpha beta unsaturated part. All right. So Professor Smith loves this reaction. There's tons of examples where you can practice seeing products like this and breaking them apart into their precursors. The reason that this reaction is important is because you can use it to make various steroids, and so this was involved in some of the early synthetic organic chemistry, and it's sort of a classic example of building up the organic chemist's favorite structure, a 6-membered ring out of simpler precursors. Notice during this whole process, we did not even talk about all of this stuff over here. Any effort you expended worrying about that would have been wasted. The way you avoid doing that is you focus on the important stuff, you look for the structural patterns. As soon as you see cyclohexenone, you can forget about all of this. In fact, if you want to erase it and replace it with R groups till the very end, you can. Okay? This is how you shut down the SpongeBobs and douse the flaming fire filing cabinets. All right. Anything else on that? So that's worth practice. Practice that until it's pretty easy for you to break apart and think backwards to what the starting materials would have been. Okay, so with that, we need to move on to the next subject, which is no longer going to be carbonyl chemistry. So you sort of survived through that. We're going to come back to carbonyl chemistry when we do metabolism. But for now, we're going to deal with something called aromaticity. And this is a special property that some organic molecules have and others don't, and it dramatically influences their reactivity, so it's important to know about. You'll recall that in 351, you learned that you can use an acid to react with an alkene as a nucleophile, where the alkene attacks the proton on the acid to give you a good leaving group. You get a carbocationic intermediate that then gets attacked by Br- to give you this product. And you may have noticed that we've done a lot of these reactions in the presence of phenyl groups, which also have double bonds. But we haven't ever shown you a product of addition of HBr to one of the double bonds of the benzene ring because it doesn't work. Benzene and HBr sit and stare at each other sort of indefinitely. Nothing happens. And so you can do these types of addition reactions to alkenes in the presence of benzene, and the benzene ring is fine. If then we conclude that the benzene ring, the pi bonds in the benzene ring are less reactive than the pi bond in the alkene, that must mean they're lower in energy. And we need to determine why. Now, in this case, you might say, well, it's conjugated, and that you get resonance stabilization. But I'm here to tell you that if you take the same number of conjugated pi bonds, I don't want to draw the products because they're complicated, but this one will react. In other words, benzene is more stable than the conjugated linear compound. Okay, so we're going to sort of do this out of order because there are some simple rules we can learn to identify compounds that have this special stability that benzene has. We're going to call that special stability aromaticity. The rules will help us recognize them. Why those rules work I'm going to hold off until a little bit later because it involves some molecular orbital stuff that's pretty straightforward to understand, but it's better if you know the rules first. Then you can appreciate learning where they came from. So molecules that have this special stability, this inertness to things that would react with alkenes, are called aromatic. Used to be that name was because some of them were smelly, but we use the term aromatic, and it has nothing to do with smell anymore. It has to do with the special stability that benzene has. So here are the rules for benzene's special stability. And then we'll apply those rules in the context of multiple reactions. It's sort of easiest to learn by considering examples. So first, a molecule that has benzene special stability, or aromaticity, depends on first being cyclic. So this linear molecule can't be aromatic because it's not cyclic. All aromatic compounds are cyclic. Second, it has to be fully conjugated. Meaning, what does fully conjugated mean? Well, we use the term conjugated to describe double bonds that are involved in resonance, or pi bonds that are adjacent to lone pair that could be involved in resonance. What this really means from an orbital point of view, a molecule that is fully conjugated must have a contiguous array. That means sort of a connected line. Dang it. Probably should have made that easier. A contiguous array or connected line of unhybridized atomic p orbitals that we're going to combine to make delocalized pi orbitals, pi molecular orbitals. Okay, so what do we mean by this? Well, notice that in benzene, each of those carbons is sp2 hybridized. You can tell that because each carbon is surrounded by 3 groups. The geometry of those carbons must be trigonal planar. The sigma bonds that each carbon makes come from sp2 orbitals on carbons. So this sigma bond from one of the sp2 orbitals, this from the other, this sigma bond from the third. What's left over is the unhybridized p orbital, right? And of course, that's where we get this pi bond from. So if we're looking down at this molecule from the top, we would see, and we're just seeing the top lobe of the p orbital. There's another one below it that we're not really going to draw. We would have p orbitals on adjacent atoms, and they're all lined up with each other side to side. Another view of this might be to look at the benzene ring from the side. Oh. And then we can draw the p orbitals this way and see that each of them is lining up with the others side to side with the same wave function sign. And this is exactly how we made pi bonds previously in 351. The difference now is that we're going to mix all 6 of these together to make some delocalized pi molecular orbitals. Stay tuned on that as to what they look like. All right? So to be aromatic, you have to have p orbitals on adjacent atoms that can line up. Cyclic, fully conjugated. Okay, questions about what that means? Yeah?
For like a cyclopentadienyl, could you have one of the pi bonds be like not between the carbons of the ring, but like between one of those carbons and the carbon?
Are you about this?
Yeah, and then the pi bond on the top there.
Oh, that's interesting. Would that be aromatic? Stay tuned on that. Yeah, because there's an answer to that question. But to answer it, we need to get to the third criteria, which is you also have to have the right number of pi electrons. This is the criteria that's most difficult to understand, and it has a reason, and the reason comes from the molecular orbitals that we're going to make by combining these contiguous p orbitals together. The explanation is pretty simple, but I'm going to hold off on the why, and you're just going to have to accept the what on faith for right now. Okay. So what is the right number of pi electrons? Molecules, and what do we mean by pi electrons? These are the ones that are involved in resonance. So 2, 4, 6 pi electrons in benzene. The number of electrons that scientists have observed are associated with aromaticity follow the following pattern. Okay, aromatic molecules always have the number of pi electrons that are within this series. Okay, so you didn't think this was a math class, and it's not, but is there a general formula for that series? It looks like you add 4 every time, right? So if I were to try to represent this series, I might say it's 4n plus 2, where n is any integer greater than or equal to 0. Understand, people get confused by this because they always want to know what is n, as though n is related to some structural feature of the molecule. It's not. N just defines the series, right? Molecules that are aromatic, we've observed experimentally, have this number, one of these numbers of pi electrons. Has to be on this list. This just defines the list of possible numbers of pi electrons that would allow you to be aromatic. The n doesn't have anything to do with the number of atoms in the ring. It just defines the series. Is anything you want to ask about that? Yeah.
If it needs to be a cyclic molecule, how is 2 possible?
If it needs to be a cyclic molecule, how is 2 possible? Sure. Well, that molecule, cyclopropene cation, would be aromatic. What we would mean by that is this is more stable than you would expect for a carbocation. And it has the added benefit of sort of looking like one of the Toy Story aliens. So, and this is a good example. Is it cyclic? Yes. Is it fully conjugated? Yes. Does it have the number of pi electrons from this list? Yes. It has 2 electrons in the pi system, and therefore it satisfies that criteria. Now we're going to see that there are molecules that are cyclic and fully conjugated, but do not have the right number of pi electrons. So we'll call this cyclopropene cation aromatic. We're still coming back here. But I wanted to point out that if you have 4n pi electrons, that is, if you have 4, 8, 12, 16, etc., not only are you not aromatic, but you are anti-aromatic. And molecules that are cyclic and fully conjugated but have this number of pi electrons have unusual instability and high reactivity. So let me give you an example of a molecule that's anti-aromatic. This is cyclopentadienyl. It's cyclic. It's fully conjugated. Each of those atoms should have a p orbital that can line up with the others side by side. So we count the number of electrons that are involved in the pi system, and we get 4. There are 4 electrons in the pi system. That means it's not aromatic, it is in fact anti-aromatic. We will learn why when we consider the molecular orbital picture. But for now, just know that if you have the number of pi electrons from this series, the molecule is highly reactive. In fact, we're going to see later that cyclobutadiene would react almost as a diradical. And I'm not going to, well, I won't write that down because I want to save that for later. Molecules that are anti-aromatic will often distort their geometry such that the conjugation isn't as strong as it once was. So if you can imagine cyclobutadiene making these sigma bonds a little bit longer, that breaks some of the conjugation. If you can imagine cyclobutadiene sort of puckering so that the pi bonds are a little bit twisted relative to each other, that would break conjugation, and that prevents it from being fully anti-aromatic. Another example of a molecule that does this is called Cycloocta Tetraene. It's the stop sign molecule that's fully conjugated, and but it has 8 electrons in the pi system. So it would be anti-aromatic because it's cyclic and fully conjugated. It just has the wrong number of pi electrons. And this molecule in practice actually distorts itself from planarity to avoid being anti-aromatic. So it adopts a structure that looks kind of like this. It folds 2 of the pi bonds opposite each other sort of up. That breaks the conjugation and makes cycloocta tetraene just sort of like a basic alkene. But the reason it does distort its geometry that way is because in its planar form it would be highly unstable, anti-aromatic. All right, let's return to your question about this molecule where you have 2, 4, 6 pi electrons, but it's not totally clear because are these part of the cycle or not? Let me ask you the question this way. That's what a politician says when he doesn't want to actually answer the question. Let me answer that by asking you this. Let's compare 2 possible resonance structures for this molecule, and then maybe you can tell me which one you like better. This one, right? Why? Okay. It has to do with number of electrons. This has 6, whereas this has 4 in the ring. So you would, I'm not sure. There is a related molecule that lacks the methyl group, sort of, or the lacks that exocyclic methylene group. It's this molecule, Cyclopentadienyl Anion. And this is aromatic because it has the right number of electrons. So I would say that this molecule has an aromatic resonance structure and an anti-aromatic resonance structure. Probably this is a bigger contributor. And probably you would observe that this molecule has a dipole. Probably it's more polar than you would expect for a hydrocarbon in order to preserve, in order to have something that's more similar to being aromatic. Okay? All right, so it's pretty straightforward when dealing with carbons. We need to answer the question, though, what do you do when there are heteroatoms? Heteroatoms are anything that's not carbon or hydrogen. So let's start with this one, 5-membered ring, 2 double bonds, and a nitrogen with a lone pair on the nitrogen. Aromatic or not? So you can sort of have 3 options. It can be aromatic, it can be anti-aromatic if it satisfies all the other criteria but just has the wrong number of electrons, or it can be plain old not aromatic. For example, this molecule that I'm going to draw here is cyclic, but it's not fully conjugated, so it's just plain old not aromatic. Anyway, the molecule on the left, aromatic or not? Go ahead.
It would be aromatic
Okay, good. Why?
because you have the fully conjugation. You also have it's cyclic.
Okay.
And then you have two electrons coming from both those pi bonds, but then you also have the extra lone pair in the nitrogen that's also contributing.
Okay. So I have 6 electrons in the pi system. How did you know that those lone pairs count?
I kind of just guessed.
You kind of guessed? Okay, fair enough. Go ahead.
Because they're technically in the ring because
Okay. They are in the ring. I mean, they're part of the ring. I think maybe you might. There you go.
take them over one.
Right, so you're recognizing that we can draw a resonance structure where the lone pair on that nitrogen is involved in a pi bond. If you can do that, then though that lone pair is involved in the pi system, okay? That because that lone pair is involved in resonance, it is part of the pi system. The other way to recognize that is a geometry argument, and it goes something like this. That nitrogen, because of resonance, must be sp2 hybridized, right? Because in this resonance structure, you have a pi bond here, and the nitrogen's sp2 hybridized. It must be sp2 hybridized here because resonance doesn't involve moving of atoms, and switching back from sp2 to sp3 would be moving atoms. So sp2 here, got to be sp2 up on top. Now, if that nitrogen is sp2 hybridized, each of these sigma bonds accounts for one of the 3 sp2 orbitals. What's left is the p orbital that would be above and below the plane of this molecule, and if those lone pairs are in a p orbital above and below the plane of the molecule, they can line up with the p orbitals on the rest of the molecule. If you want to view this molecule from the side to get an idea of sort of what we're talking about, what we're saying is the lone pair on that nitrogen is held in this kind of orbital where it can overlap with the p orbitals involved in those other pi bonds. Okay? That's how you tell whether a lone pair is part of the pi system. Now, let's make it a little trickier. Ooh. No. Aromatic or not? Well, let's go through the list. Cyclic, sure. Conjugated, sure. Number of pi electrons. There's a controversy. I heard somebody say 8, and somebody said 6, right? If you said 8, you're probably going double bond 2, other double bond 4, this lone pair 6, and you're probably counting that one too. Okay, go ahead. You can delocalize the one that's next to the double bond, yes. Here. You can't delocalize that. Why not? Okay, yeah. Good. I'm sorry, I didn't realize that was a question. The other day, some folks were in my office, and one of the TAs came to ask a question, and she wanted to draw something on the board, and she said, "You don't need to move," but the student heard, "You need to move," and so he jumped up right away, and then she felt kind of like, "Oh, I never would have said that," but I was like, "Way to be assertive! You need to move." Anyway, I misheard. Yeah. So what about these electrons? Do they count? I mean, these are in the same situation as up there, right? It's clear that these count because we could draw a resonance structure in which we delocalize them, right? If they can be involved in resonance, then they're part of the pi system. And the question is, what about over here? Can I draw a resonance structure? Why am I struggling with that? There we go. Can I draw a resonance structure where I do that? Why not? What's wrong with that? You laugh, but you might be tempted to do it on the exam when you're stressed and hungry and worried and the testing center's about to close. That might suddenly look way more reasonable to you than it actually is. What's wrong with that? You got 5 bonds to carbon. Could it go the other way? Okay, let's do that. So you want to move this over to there. So there's a reason this doesn't work. There's 2 reasons it doesn't work. First, you just proposed a nitrogen bonded to 4 things. That would need to be sp hybridized linear, and it can't be in a 5-membered ring. But there's a more fundamental reason why that doesn't work. And the answer has to do with, again, which atomic orbitals are contributing to bonds versus lone pairs. So the nitrogen is involved in a pi bond, therefore the nitrogen's sp2 hybridized, right? We can agree on that. Therefore, let's see, what atomic orbitals, an sp2 hybridized atom comes with 3 sp2 orbitals and 1 p orbital. The p orbital has to be involved with this pi bond because that's where pi bonds come from. So we've got that one. One of the sp2 orbitals is involved in this sigma bond. The other is involved in that sigma bond. So we've got 2 of the 3. That lone pair must be in an sp2 orbital. Does that make sense, sort of walking through it that way? It can't be in the p orbital because you're already using the p orbital for the pi bond. All right, what will that mean in terms of the structure? Well, if we look at this molecule and sort of view it from the side, we would see that lone pairs on the nitrogen on the left can indeed be in a p orbital that lines up with the other p orbitals in the molecule, but the lone pair on the nitrogen, I said left, but I meant right. I told you I get that wrong every time the first time, right? Sorry. I'll correct that next time, but the lone pairs here are in an sp2 orbital. They can't line up with the p orbitals of the pi system, and therefore they can't be involved in resonance. They don't count. So this molecule is aromatic. Okay, we'll come back to that next time.
Can I just make sure I understand that?